Measurable sets are nice sets. We need measurable sets to rule out the Banach-Tarski Paradox, which relies on non-measurable sets. E is a measurable set, has a kind of a strange definition. A is any set. The outer measure of A is split into two pieces by E. This is set difference, whichever notation you want. Another way of saying this is that if I rewrite A as a disjoint union, when I measure each piece separately, it's the same as the union. This is countable additivity as opposed to subadditivity. Splitting a finite union into pieces that has the same measure, this is a property of a measurable set, that this split happens. The Banach-Tarski Paradox uses this property on non-measurable sets to double the size of the sphere. Let's use our simple graph paper measure to illustrate a measurable set. I'll stick to the grid lines. That set is measurable. Call it E. So now I'll take any other set in the plane and look at its measure by counting the squares that cover it. The squares that are colored are the squares that I count. The blue squares and the green squares. Every square has only one color, so every square is only counted once. The measure of A is the measure of the blue squares plus the measure of the green squares. I have countable additivity. To look at what a non-measurable set looks like, just modify my set E slightly, redraw A. Now, that modified square is counted twice. It's blue and it's green, so that square is counted for the intersection and it's counted for the complement. So the measure of A is now strictly less than the measure of the sum. So E is not a measurable set. The first stage in proving that they're desirable is that they're closed under unions. So I have two measurable sets. I want to show their union is measurable. Here's a trick. There's a couple tricks for this proof. One is I'm going to apply measurability of E2 to the set A intersect E1 complement. It seems unmotivated at the moment, but in a second it will be clear why this is used. Now we'll look at the union, and subadditivity gives us this relationship. E1 complement E2. There's the other trick. That the intersection of A1 with the union is A intersect E1 union A intersect E1 complement intersect E2. Now we can put them together to show the reverse inequality of subadditivity. A intersect the union and A intersect the union complement. This is less than or equal to, copying the line above, plus rewriting the union complement in terms of the complement intersections, one of our De Morgan's laws. Now we're all set. By the measurability of E2, those two combine. And that's our first line that was mysterious. And by the measurability of E1, those two combine, and we're finished.